In this lab, the exemplification of Newton's second law and the basic concepts of velocity and position are represented. In this experiment, a ping pong ball was used as an example, and we determined its velocity through the tracker program. The video of the ping pong ball trial is seen here, where the ball travels at a constant velocity for a given duration of time. We must crop out some of the time intervals in the beginning and ending in order to achieve a sample of constant motion, as the ball holds changes in acceleration in the beginning and ending of the video. We then made a computational model of the motion using Python. Through Tracker, we were able to determine the positions during two different time frames. Using the equation, we find the average velocity of the motion. Plugging in the velocity to the code and making a multitude of changes to the model, such as changing the net force to 0, and applying Newton's second law, we get the predicted model of motion of the ping pong ball as seen here. The ball is moving to the right, therefore the velocity is in the positive direction. However, if we flip the axes, the ball would be in the negative direction. The initial number for the push of the ball must be equal to the number of force pulling the ball by friction in order to create zero net force. So it is indeed possible for one to say how many pushes or pulls are added together to create zero net force. Finally, we compare the results of the computational model to the motion seen in Tracker. We graphed both the predicted and observed models and aligned them. Since we cropped out the beginning time interval of the Tracker trial, the Tracker model does not start when t equals 0. However, since we are only looking at the concept of constant motion and Newton's second law, the emphasis is only seen on the slope of the line, and not necessarily the initial position. We find that when comparing the two slopes of the line, the predicted and observed motions are very similar. However, as time moves on, we can see that due to friction, the ball begins to slow down and its constant motion is lost, creating a slight curve at the ending points of the Tracker data. Since the computational model does not account for friction and only holds a constant motion, there is a contrast between the two graphs as seen. Though the Tracker data holds true for a period of time, it is not a good representation of constant motion for a prolonged period of time. In conclusion, we can say that Newton's second law, an equation application of final velocity equaling the initial velocity plus the net force over mass times time, stands true in this lab. Utilizing Tracker to determine the position of the ball in the sample and using Python to visually express predicted motion, we find how physics is seen and can be applied in real-life situations.